We're going to be taking a look at an important building block part, and that is the magnitude comparator. Okay, in this particular example, what we're going to do is we're going to take a look at 4-bit unsigned numbers and compare them. Okay, so here's an example. We have A equals 1, 0, 1, 1. B is equal to 0, 1, 1, 0. We know how those numbers compare. A is obviously greater than B. All right, so what I want you to do is use this infographic and take a look and make sure you understand the process. We're going to start with a single bit case. All right, so let's take a single bit, A and B, and take a look at whether A is greater than B, A is equal to B, or A is less than B. All right, so here's the truth table. When they're both 0, obviously A is equal to B. When I have 0, 1, the output is A less than B. When it's 1, 0, the output is A greater than B. And then again, when they're both the same at 1, A is equal to B. All right, so we know how we do this as humans. We take a look at, say, a 4-bit number, and we scan our way down from the most significant bit down to the least significant bit. So let's do some test cases. You can play around with this infographic. Press the C button, and you get various cases. All right, so here's a case where I have A equals 0, 1, 0, 1, and B is 0, 1, 0, 1. These match in every bit position, but you start over here at MSB and you work your way down. And since they always match, you have A is equal to B. All right, let's do another one. Let's do one where it takes a few bits to resolve. Okay, so in this case, we have 1, 0, 1, 0 compared to 1, 0, 0, 1. We can start in the MSB position. These are the same. All right, so we can't tell whether A is greater than B yet. Then we move down. These two bits are the same. And then finally, when we get to bit position 1, we have A equal 1 and B equals 0. That means A will always win. A is greater than B. That's the process. Okay, so that's the process for 4 bits. You can easily extend that to larger bit sizes. Okay, so when we look at these building block parts, we have this cadence. We want to know the functionality. We know the functionality of comparing numbers. That's not in question here. What I want to build up is how do you implement this with hardware? Okay, so taking a look at that, what we're going to do is we're going to use a staged approach where we use the equivalence gate. And remember, an equivalence gate is just an exclusive OR with a complement at the top, so an exclusive NOR. All right, and so the way that would work is if A3 and B3 are the same, if they're equivalent, if they're both 0 or they're both 1, this output turns into a 1. If they're different, the output turns into a 0. So let's take a look at this case that's illustrated here. We have A is equal to 1, 0, 1, 0. B is equal to 1, 0, 0, 1. These match in the upper 2 bit positions. And so that's shown here at the output of this exclusive OR array, where x3 is equal to 1 and x2 is equal to 1. Both those are there because those bits match. The other 2 bit positions, they don't match, so this would be a 0. From there, what we need to do is we need to figure out what should we assign the output. Okay, so in this particular case, what we have is a sequence of AND gates. All right, so we start in essentially the most significant bit position, A3 ANDed with, it's really light here, but that's B3 bar. Okay, and because these are different, these are the same, A3 and B3 are the same, A3 ANDed with B3 bar is going to be a 0. All right, so I get 0 for this gate. Same thing with the second bit position. I have A2 ANDed with B2 bar. Plug in this example. Also, x3 is equal to 1, so that gate's enabled, but these are different, so that means the AND gate's off. All right, then finally we get to this position where we have both x3 and x2 on. What that indicates is that there was a tie at the upper 2 bit positions, and then I have A1 ANDed with B1 bar. In this particular case, B1 is a 0, so B1 bar is a 1. That means the A wins. Okay, and so I turn on a 1 here, and I get this going through, straight through to A greater than B. All right, so that's the basic idea. is that you look at this and you compare whether there's a bit that's tied, and you resolve the tie all the way down. Okay, so we can do a couple of other cases here and press the C button or click on this, and you get a case where A is less than B. Okay, so basically the idea with A less than B is you still form the XOR array, and then you test, is A greater than B? If it's not, you have two possibilities. One possibility is that A is equal to B. Well, we know that's not true, because for that to be true, all these have to match. Okay, and so this one's off, and so that means this term is a 0. Okay, then I have two zeros here. That means from an equivalence gate, this would be a 1. So that's the tricky case to me, is A less than B. The idea here is you check, is A greater than B? And you also check, is A equal to B? If that's not the case, then you assert A is less than B. Okay, so you can go through and take a look at other cases. When you have equality, all these outputs from the exclusive OR array turn on, and you light up A is equal to B. All right, so that's how the hardware works. I think it's important to have a mental model of how the hardware works for different building block parts. Okay, there's lots of applications of magnitude comparators. Sometimes you want to compare it to a threshold. Address decoding has some aspect of magnitude comparison. CPU branch conditions, all these things are important for actual working digital hardware. The next thing I want to show you is the Verilog implementation. Okay, so we define a module as we did before, where we have a bit size. In this case, this is 4-bit numbers. And then we have to define outputs. All right, I make these reges because I'm going to use an always block to assign greater than, equal, and less than. Okay, so I have an always block that we've discussed a little bit. And then the first thing we do is we take care of the default. So we default everything to 0 so that we don't accidentally create a latch. That's good Verilog coding practice. And then we just go through some if statements. If is A greater than B, then we assign greater than. Else if A less than B, we assign less than. Then that would fall through to the equal case, just like we know how if and else blocks work. We could use the case statement as well. All right, so there's the Verilog description. And for those of you who like really cryptic code, I wanted to show you this. This is also a way that you can get equality. So you can have a vectorized, a bitwise exclusive NOR, and then reduce it at the end. That's just showing you it's possible to do things in an encrypted way. I don't expect you to know that. Okay. The other thing I want to mention here is the way this is done, we haven't talked about 2's complement and negative numbers. This is definitely for comparing unsigned numbers. All right. So we'll get to signed comparisons a little bit later. All right. So the magnitude comparator, it's important to know these 4 steps. The functionality, comparison's easy. We know what comparators do. The hardware design, and then we know that there's lots of applications, and we would be able to recognize a Verilog description if we saw one.